Hello, this is Jared Nemi with a mini lecture on missing data in the notation that we can use for survey sampling and for randomized experiments in the context of design-based inference. So the main thing we're going to be interested in here is determining how to construct the complete data and understand what the missing data is, what the observed data are, um, and what the inclusion indicator matrix is. Okay, so the main start from this is to think about missing data differently in different contexts. So from table 7.1 in Bayesian data analysis, we can think about observed data and complete data in a number of different scenarios. The first scenario being in survey sampling, where you have a total of capital N units in the entire population. That would be your complete data if you observed all of those units, but you typically don't. You observe some sample of those units, and we'll call that lowercase n. So your observed data here is that sample, and your complete data is the whole population. Another example is that used in experimental design, where you have a certain number of units, and those units are going to get assigned a treatment. And so your observed data is that unit under that treatment, but your complete data would be that unit under all of the possible treatments. Another example is sort of centered data, in this case rounded data, where what you actually have are the rounded observations, and the complete data would then be the actual precise values of the observations. Last one here is unintentional missing data, where you have whatever it is you've observed, and there's some missing data there, and that missing data, together with the observed data that you have, make the complete data. Okay, so just introduce some notation here. We have capital N units in the population. We have a sample of size lowercase n. And we have the complete data. Here we have y is a vector or a matrix of elements y1 up to y capital N. That is, if we observed all of the individuals in the population, where each of these y's right here could itself be a vector. So if you observe multiple values on a particular observation, then we could have y1, yi1 up to yij, if there were j different measurements. Alright, so now we're going to have an inclusion indicator matrix that's exactly the same size as y. And so in this case, we have a vector or a matrix here of I1 up to capital N, and then each of those sub-vectors or subscalars could be a vector itself. So I subscript little I1 up to capital I subscript little ij. And this inclusion indicator is only a 0, 1 for every element in this matrix. And so it's a 1 if the observation itself, the y that's associated with, was in fact observed, and a 0 otherwise. And then we'll break these up into two different groups and call the set of ij in this inclusion indicator matrix that's 1, we're going to call that obs. So we're going to later say y subscript obs, and that's all of the observations we actually have. And the opposite of that are the missing, and that's the locations where the inclusion matrix itself is 0. Alright, so again, this inclusion matrix just tells us of this possible complete data, which elements of that data do we observe. And typically this I itself is in fact known. Alright, we also have the possibility of having some covariates on each of the units. This is not really going to come into play in the examples I'm going to show in this mini lecture, but the notation is generic enough that if you had covariates for the units, then we'll incorporate them with this x, where x1 again could be, okay, so I didn't put it here, the x1 and up to x capital N itself, each of those could itself be a vector, not necessarily the same size j here, because of course we could have different number of covariates than we had of the response that we're interested in. Okay, so here typically we write the model, the joint model here for the complete data y and the inclusion matrix I, conditioned on the covariates and these parameters theta and phi, and we usually can decompose this into a conditional distribution for I given y and x and the parameters phi. So these parameters phi only determine through the complete data y and the covariates x this inclusion probability matrix, although the I could itself be random, right? Thus a probability distribution. And then the data, the complete data, only depends on x and some other parameters theta. Notice here, if we had the complete data, then we would not need the inclusions in order to make inference about theta. Okay, so that's the complete data model, and what we'd be interested in typically is the posterior in this format, where now anything that's unknown is a random variable, and it comes into play in our posterior. So obviously our parameters theta and phi here are unknown, but also all of our missing data is unknown. And we can write this as proportional to the complete data model. Alright, so I should in fact have the prior on here for theta and for phi. Yes, so over here there should be a prior on theta and phi. I'll fix that in the slides that I send out later. But that would then be the full posterior that we're interested in. Okay. Alright, so we are often only interested in this marginal posterior for theta. That is, we want to know what we know about theta, right here, that is the relationship between the covariates x and our responses y. Right, if we have no covariates, these are things like the population mean or the population standard deviation. So we want to know something about theta, and what we have are the covariates x, our observed data y, and the inclusion indicator matrix. And so we can write this out here, where now we have the same piece right here that we had before. We have this product of the complete data likelihood and the inclusion matrix probability distribution conditional on the complete data. And now we've split up the prior on theta and phi into the conditional prior for phi given theta, and then the prior for theta given x. Right, so we're going to take this piece, and now we're going to integrate out the missing data and our parameters phi, because in this marginal posterior, we're just not interested in them. Okay, so this is now going to be a definition. So if it's true that the parameters theta, if it's true that the posterior for theta that we're interested in here does not depend on the inclusion matrix I, then the process or the model, the design, is called ignorable. Alright, so the only key here thing is that the posterior for theta conditional on I is conditionally independent given x and y obs. Alright, so there's two important... Alright, sorry, before I get there, and we could then write this now as a function where we do not need the phi piece or the indicator piece because the posterior for theta doesn't depend on I. Alright, so there's two key pieces of, or two conditions that will ensure this ignorability condition are true. The first one is that if the data, if the inclusion probabilities, or the data that are missing at random. And so formally we could define right here our probability distribution for the inclusion matrix as conditional on x, the complete data y, and some parameters phi. So we've written that here. And if it turns out that the inclusion matrix does not depend on the missing data, so that it's conditionally independent, given x, y, obs, and phi, if it's conditionally independent of the missing data, then this is called missing at random. So that's the first condition. And the second condition is that the parameters themselves are distinct in the prior. So phi does not depend on theta in the prior, conditional on covariates x. So as mentioned in Bayesian data analysis, oftentimes the key thing here is to make the covariates x large enough so that this condition is true. Alright. So the convenient aspect here is that if the process is in fact ignorable, then we can use this right here, right? This right here, this posterior right here that only depends on the observed values as our posterior for theta because it's equal to this posterior that we actually have, or that we're interested in. Okay, so I'm going to give two specific examples, one in the survey approach and one in the experimental design approach. about how this all comes together. So the first one here is just simple random sampling, where you have capital N individuals in the population, and you're going to randomly sample them without replacement for a total of small n units. And since we have no additional information on the units, there are no covariates in this example. Alright, so then we can write down our inclusion probability matrix I and the probability distribution for this matrix I, typically as a function of the complete data y and phi, but we'll notice in a second that it does not actually depend on the complete data, or any of the data for that matter, or any other parameters. Alright, so here it is, and I'm going to run through why this is actually true. Alright, so the first part of the result, this part right here, this n choose 2, or sorry, little n choose capital N. Alright, let me say that again. We have capital N units, and we're going to choose little n units. Alright, and so the idea here is that is how many ways there are to choose little n objects from capital N objects. And so each of these inclusion probabilities, the ones that are actually reasonable, each one of those is going to have 1 over that quantity probability. Alright, and so, so each inclusion that has exactly little n ones, that is, that we've actually sampled little n individuals out of this population of capital N individuals, has probability that's 1 over the number of different ways there are to choose that sample. And now the key piece is that we need to restrict and only allow I to have n ones, so that any designs that happen to have more or less than exactly n ones in this inclusion matrix have probability 0. That's this piece right here. Right, so this piece right here says that only the times when we picked exactly little n units of the population, it has this probability, and otherwise it has 0 probability. Right, so the idea here is that there's 0 probability given to sampling 0 units, or 0 probability sampling all of the individuals. 0 probability of sampling n plus 1, right? Because we know we've sampled exactly little n of them. Alright, so it turns out, I didn't mention this, so this design is ignorable, and in fact it's strongly ignorable. And I didn't mention strongly, but I'll just mention that this design is. So the idea here is that now we can just use the posterior for theta conditional on the observed data and get exactly the inference that we need because the design is ignorable. Alright, so I want to give a particular example of the simple random sampling just to make sure this inclusion probability matrix part makes sense. So we're just going to imagine that there's 4 units on the population and that you're sampling 2 of them. Alright, and so the idea here is, here are the possibilities for this inclusion vector I. Right, it has 4 elements, 1 for each unit in the population, and it's going to have 2 1s and 2 zeros, because we're going to have sampled 2 of the individuals and have not sampled 2 of the individuals. So these right here on the left side are the 4 possibilities are the 6 possibilities for the inclusion vector of sampling exactly 2 individuals out of a population of 4 individuals. There are 6 of them, so each of them has exactly 1/6 probability. But note here that we could have enumerated all the different possibilities of 4 zeros and 1s. Right, there's going to be 2 to the 4th of those. But because of the inclusion probability distribution on the previous page, all of those vectors that don't have exactly 2 1s and exactly 2 zeros will have probability 0. Right, so for instance, right, this is sampling no individuals from the population, this is sampling all of the individuals from the population, and these do not coincide with the fact that we know we sampled exactly 2 of them. Okay. Here's an example from randomized experiments. So this is slightly different from the completely randomized experiment described in Gelman. The idea here is that we just have little n units in our sample, and then each one of those units is going to be randomly given 1 of k possible treatments. Right? So I here is now an n by k binary matrix with each row summing to 1. So here's the idea. The idea is that each row is an indicator. Each row has k columns, and that indicator says which treatment individual in that row received. So it's going to have a 1 in one of those columns and a 0 everywhere else. So another way to say that is each row sums to 1. Again, in this example, there's no covariates to distinguish the units. And we can write then the inclusion probability distribution as this. So again, we're initially conditioning on the complete data y and some parameters phi. It turns out again that this is going to be independent of y and phi. And so here we have 1 over k to the n, and this is just the constraint that each row sums to 1. Right, so if the row doesn't sum to 1, if we for some reason think that a particular unit had 0 treatments or it had more than 1 treatment, then the probability of that is 0 because we know that exactly 1 treatment is given to each unit. Right, so as I just said, each unit gets exactly 1 of k possible treatments. Don't know why that's there. Each unit can only receive 1 treatment. That's this constraint. Oh, I guess the point here is that the probability of getting treatment 1 versus treatment 2 versus treatment 3, each one of those has 1 over k probability. Right, so for each individual unit, there's 1 over k probability on the k possible treatments. And we've done this now independently, and so the probability for the joint probability for all units is just the product of the individual probabilities for a single unit. So each unit has 1 over k probability on each of its possible treatments, and since they're independent, then we have 1 over k all raised to the nth power, or 1 over k to the negative n, or sorry, k to the negative n. Okay, so again, this design itself is ignorable, and again, strongly ignorable. So to give a particular example, here let's imagine that we have 4 units again, and now we have 2 treatments. We're going to call these treatments A and B. I want to mention that here's what the actual inclusion probability matrix looks like. So each row here represents a particular unit, and each column represents a particular treatment. So in this example, the first unit got treatment A, B, and then A. Right, so the third unit got treatment B, all the other units got treatment A. Alright, so in what I'm going to write below now, instead of writing out this inclusion matrix for all the possible different designs that could have occurred, I'm just going to use A and B to denote which treatment each unit received. So here are the possibilities. All the units received treatment A, the first 3 A and then B, 2 A's B, A, and so forth. If we write all those down, it turns out that there are exactly 16 different possibilities, and each of those are equally likely, so there's 1 out of 16 probability on each of the units. Equivalently, on the last page we saw that it's 1 over k to the n, right? K here is 2, 2 to the 4th is 16, 1 over that is 1 over 16. Right, and again, there are other possibilities of this inclusion matrix here, that is, if there's a 1 and a 1, or a 0 and a 0, but because of our the restrictions on our probability distribution over the inclusion matrix, any of those possibilities all have probability 0. Right? So if a unit has 0, 2, or more treatments, that has probability 0. Alright, so this was just a couple examples of the setting up design-based inference. Alright, so I discussed some terminology in the construction of this inclusion indicator matrix and how to think about its probability distribution. The main thing is to think about that this inclusion probability matrix is a discrete, it's going to have a discrete distribution. Each element in the matrix is going to have support 0 and 1. Right, so it's binary, it's a binary, each element is binary. Alright. Then Gelman makes the comment here that, well, he's responding to a comment that many people say that Bayesian analysis does not depend on the design, in contrast to some other modes of inference. And so he wants to clarify that this is true if the design is ignorable. But it's only true to the extent that the posterior distribution of the parameters, ends of functions of those parameters, with a fixed model, right, and prior, those don't depend on the design. Right, so the posterior of the parameters don't depend on the design if the design is ignorable. So this says here that if the design is non-ignorable, then Bayesian inference needs to include the design, even to determine the posterior distribution of parameters in a particular model. But it also says that anything other than just the posterior, such as a sensitivity analysis looking at different priors and posterior predictive checks, these will depend on the design. All right. Thank you.